So far, we've learned what K sub C and K sub P are, but the size of the K value, the magnitude of it, also tells us something. It indicates the extent to which the reactants are converted to products, or essentially it tells us the reaction side that's favored at equilibrium. So if you have a small value for your K, a value much less than 1, we say that this is a reactant favored equilibria. That means that when the reaction reaches equilibrium, there will be a lot more reactants than there will products. If we have a K value that's equal to 1 or about equal to 1, neither side is really favored. That means that at equilibrium, there will be about equal amounts of reactants and products present. And if you have a large value for K, a K that's much bigger than 1, we say this is a product-favored equilibrium. Once the reaction reaches equilibrium, there should be a large amount of products and a small amount of reactants. As the value of K gets larger, that means that the reaction proceeds farther to the right. And when we say farther to the right, we mean it produces more products before reaching equilibrium. So in this range of about 10 to the minus third through 10 to the positive third, that's what we consider to be about equal to 1. Within that range, you'll have about equal amounts of reactants and products present when the reaction reaches equilibrium. They won't necessarily be equal to one another, but you'll have an appreciable concentration of both of them. If you have a K sub C or K sub P that's very, very small, that means the reaction really doesn't proceed very much. You're going to have mostly reactants present and not very many products. On the other hand, if you have a KC or K sub P that's very large, the reaction will proceed to pretty much completion. That means you'll have mostly products present at equilibrium and not very many reactants left. So it's a sliding scale, and anywhere in between the very small and about equal to 1, you're still going to have mostly reactants present, but you could start forming some products. Then when you're within this range, you'll have about equal amounts of reactants and products. And then anything outside, getting larger and larger and larger for your K value, you're going to start making more and more products when the reaction reaches equilibrium. If we were to combine random amounts of reactants and products in a flask and seal it, how could we tell the direction the reaction will proceed? Will it shift to the left and make more reactants, or will it shift to the right and make more products? This is if we're putting non-equilibrium amounts in our flask. So we're just putting some random amounts in there and seeing what will happen. Essentially, a system will react to achieve the ratio of products to reactants that's expected of the equilibrium constant, meaning K sub C or K sub P. So we can figure out what way a reaction will shift either to the reactants or to the products in order to attain equilibrium. In order to determine the direction a reaction will shift, we compare the equilibrium constant to something known as the reaction quotient. The symbol for the reaction quotient is capital Q. The reaction quotient is defined in the exact same way as the equilibrium constant. Imagine we have this reaction again of A plus B forming C plus D. We still would take the ratio of the product's concentration over the reactant's concentration and raise them to the powers from the balanced equation. So lowercase a, b, c, and d represent coefficients. Only now when we plug in to these concentrations, we're going to plug in non-equilibrium concentrations. Anytime we put something into the mass action expression that's not an equilibrium concentration, it'll now be equal to the reaction quotient. We can use the value of K sub P and K sub C with the value of the reaction quotient in order to predict the direction that the system must shift to attain equilibrium. One of three things could happen. We could calculate Q, and it could be exactly equal to K. If that's the case, the reaction is already in equilibrium because Q and K are the same. No shift would occur. Or we could have the value of Q less than K. If K is bigger than Q, the reaction quotient must get bigger, or Q must increase in order to be equal to the equilibrium constant. Q is equal to the ratio of the products over the reactants. And how are we going to make the value of Q get larger? The only way Q will get larger is if the numerator of that fraction increases or we make more products. In this case, we would say that the equilibrium needs to shift to the right. When we say to the right, we mean to the products. If we make more products, Q will get bigger until it reaches the value of K. The last situation we could have is where K is less than Q, or in other words, Q is bigger than K. In this example, Q must decrease. So Q needs to get smaller. And if we think about our fraction of what Q is, the ratio of the products over the reactants, the only way that we can make the value of Q get smaller is if we increase what's in the denominator, or our reactant concentration. So in this case, we would say that the reaction needs to shift left. And when we say shift left, that means towards the reactants. So depending upon what the value of Q is, comparing that to the equilibrium constant K, we can decide if the reaction is going to move towards the products to the right or towards the reactants to the left in order to attain equilibrium. If Q is already equal to K, in that situation, no shift would occur because the reaction is already at equilibrium. Consider the reaction H2 gas plus I2 gas forming 2HI gas. We have the value of K sub C, which is 57 at 700 Kelvin. We don't need to use that 700 Kelvin. It's just given to us because the value of K is only good at that temperature. Also notice that our value of K sub C is in the range of 1 times 10 to the minus third through 1 times 10 to the positive third. So that means that at equilibrium, there's going to be an appreciable amount of reactants and products present. It's not a reactant-favored equilibrium or really a product-favored equilibrium. So if we have a mixture with the following concentrations, is the reaction at equilibrium? If not, what direction must the reaction proceed, either left or right, to attain equilibrium? So we're given non-equilibrium concentrations. So that means that first we're going to calculate Q, the reaction quotient, and then compare it to our known value for K. H2 is equal to 0.1 molar, I2 is equal to 0.2 molar, HI is equal to 0.4 molar. So our Q can be calculated in the same way that our K was. We take our products, which is HI, and we're going to have to square it because there's a 2 in the balanced equation, over our reactants. H2 concentration to the first power times I2 concentration to the first power. Now let's substitute our non-equilibrium concentrations in. HI is going to be 0.4 molar, and we have to square that, over H2, which is 0.1 molar, times I2, which is 0.2 molar. So when we calculate Q, we end up getting 8. So at this point, we can say that Q is not equal to K sub C because 8 does not equal 57. So therefore, we're not at equilibrium. Next, we're going to analyze how the reaction has to shift in order to attain equilibrium. Does it have to make more products or does it have to make more reactants? In this case, Q is less than our K value, K sub C. So if we think about, once again, what Q is equal to our products over our reactant concentration, and we need Q to get larger. So we need to essentially make our value of Q bigger in order to match that of K sub C. How are we going to make our value of Q bigger? If we increase our numerator or if we increase our denominator? We want to increase our numerator or our product amount in order to make Q larger. So if that's the case, we would shift to the products, or in other words, shift to the right-hand side in order to attain equilibrium. Let's try another example. Consider the following reaction. 2HCl gas forming H2 gas plus Cl2 gas. K sub P is equal to 1.96 times 10 to the negative 9th at 1000 Kelvin. Once again, we don't need to use that 1000 Kelvin anywhere, but our Kp is only good at that temperature. And notice we have a really small value for our K sub P, 1 times 10 to the minus 9th. So since this is really small, that means that at equilibrium, we would have mostly reactants present, or it's a reactant-favored equilibria. Now suppose we have 0.2 atmospheres of each gas and we add them to a flask at 1000 Kelvin. These are non-equilibrium concentrations, so we have to figure out what our reaction quotient is. And then what direction will the equilibrium shift to attain equilibrium, left or right? Will it need to make more reactants or more products? So Q will be equal to, and since we have a K sub P, we're going to use partial pressures. The partial pressure of our products, so partial pressure of H2 times the partial pressure of Cl2 over the partial pressure of our reactants, which we just have one, HCl. But we have to remember to square that because there's a 2 in front of it in the balanced equation. Now substituting in 0.2 atmospheres for everything, we have 0.2 atm times 0.2 atm on the top over 0.2 atm squared in the denominator. When we calculate Q, that ends up coming out to 1. So first, we can say that 1 is not equal to 1.96 times 10 to the negative 9th, or in other words, Q is not equal to K sub P. Therefore, that means this reaction is not at equilibrium. Now, what direction will the reaction shift, left or right? Will we need to make more reactants or more products? In this case, Q is greater than K sub P. Q is much bigger than K sub P because it's so small. So when we think about what needs to happen to Q, Q is the ratio of our products over our reactants. Q needs to get smaller in this case, or decrease. And how are we going to make Q smaller when we think about what the fraction is? We don't want to make the numerator bigger because that will just make Q get bigger and bigger. If we make the denominator larger though, then Q will get smaller. So the denominator is our reactants. So we need to shift the reaction towards reactants, or in other words, that means shift to the left. So shifting to the left or shifting towards the reactants means we're going to increase the amount of reactants at equilibrium and essentially decrease the amount of products.